Hello everyone, I'm Barbara Sant'Angelo. In this video, I will talk about my work presented at the 2018 Neuroreceptor Mapping Meeting in London on how to extend the use of an existing pipeline for modeling arterial input functions to noisy blood datasets measured with a PETMR-compatible blood sampler. First, let me just give you a bit of background about a standard dynamic brain PET experiment. Full quantification of dynamic PET data often requires the measurement of the radiotracer activity in the arterial blood measured as a function of time. In general, this cannot be derived from PET images directly, but it must be measured from blood samples taken from the subject radial artery. In bolus injection PET experiments, blood samples are typically acquired manually and automatically. The automated blood sampling lasts approximately 15 minutes after the tracer injection, and it is performed by using a continuous blood sampling device, where blood is pumped at a constant rate through a well-shielded radiation detector. These blood measures need to be fitted with multi-exponential models to generate a time-continuous, noise-free curve that is used as blood-to-tissue delivery function, also called parent plasma input function, of the tissue compartmental model that drives the data quantification. Nowadays, many centers use simultaneous PET-MR scanners instead of the standard PET-CT scanners. In this case, accurate measures of automatic blood data and the modeling of the parent plasma input function are even more challenging due to the complication of working in a strong magnetic field that leads to noisier data in comparison to standard acquisition with PET-CT. Here, the need to extend the use of an existing pipeline for modeling arterial input functions called multi-blood to noisy blood datasets measured with a PETMR-compatible blood sampler. Multi-blood is a unified framework designed to perform a fully automated plasma metabolite correction and noise-free time-continuous description of the plasma tracer kinetics. On the slide, you can see a summary of the multi-blood pipeline. Briefly, multi-blood takes as input the raw total plasma concentration and the plasma parent fraction. The latter is defined by the ratio between the parent concentration in plasma and the raw total plasma concentration. From these two inputs, multi-blood returns an initial approximation of the parent plasma input function, in figure A, and an approximation of the radiometabolites concentration, figure B, which are both fit with a multi-exponential model. Then multi-blood generates the model for the plasma parent function, figure C, by combining the initial approximation of the parent plasma input function and the approximation of the radiometabolites concentration. Finally, multi-blood returns the parent plasma input function in figure D. The first applications of multi-blood to blood data were done using Monte Carlo simulations based on two continuous blood sampling systems, analog and twilight. While the analog system is representative of a variety of systems used with PET-CT imaging, the twilight system is the only commercially available product usable for simultaneous PET-MR scanners. Analytic functions to describe ground truth arterial whole blood and plasma concentrations were created based on representative data from a previous 18FG179 PET study. Poisson noise was added according to the measured specifications of the analog and twilight samplers to simulate 1,000 noisy whole blood datasets. Due to the high background noise of the twilight system, background correction was simulated in three different ways: as a constant, corresponding to the ground truth background, and as a mean taken either from 900 and 3,600 seconds of simulated data, respectively. For the input of multi-blood, as per typical scanning protocol, continuous blood data was simulated for the first 15 minutes following injection. The second application of multi-blood was done in blood data measured from two datasets of dynamic 18FG179 PET scans. The first dataset contains scans of 9 healthy volunteers acquired with a PET-CT scanner and dialog system. The second dataset contains 10 healthy volunteers scans acquired with a Siemens simultaneous PET-MR scanner and the Twilight system. In the simulations, we compared the model data with the ground truth values by using the percentage bias of the area under the blood time activity curve as a performance index. The peak of the blood arterial input function, defined by the first minutes of acquisition, and the tail of the blood arterial input function, from 5 to 90 minutes, were also analyzed separately, as they represent the most sensitive parts of the curve for the blood modeling. What we found was that for the whole blood and parent plasma data, the mean relative difference of the area under the blood time activity curve between the model data and the ground truth values were negligible, and we did not observe differences between the multi-blood results from the two types of simulated blood samplers. As you can see from the table, the performance of multi-blood is also not affected by background noise. On the left-hand side of the slide, you can see an examples of measured data modeling for the two blood samplers. Whereas on the right-hand side, I reported the results of the statistical analysis on the measured data. In particular, we compared the area under the blood time activity curves for PET-CT-derived arterial input functions with those of PET-MR-derived arterial input functions by using two-way ANOVA analysis. To account for intersubject differences, the arterial blood measures were analyzed using standardized uptake values, but normalizing its raw measure by body weight and tracer-injected dose. What we found was that for both the two systems, multi-blood returned an adequate description of the data, both continuous and manual samples, consistently for all the subjects. For parent plasma and whole blood measures, the analysis of the area under the blood time activity curve showed no differences between 18FG179 blood data acquired with PET-CT scanner compared to the ones acquired with a PET-MR scanner. These results were consistent even when peak and tail were investigated separately for both whole blood and parent plasma. To conclude, this study shows that the multi-blood method can be successfully used for modeling arterial blood data acquired with an MR-compatible blood sampler. Despite the high background noise of this class of devices, the time-continuous descriptions of the tracer activity in blood and plasma are comparable with the ones obtained in a standard PET-CT acquisition. And this result was confirmed by both simulated and measured 18FG179 PET data. Of course, alternative pipelines for arterial blood data modeling exist. However, they lack consistency and are not physiologically informed. Moreover, these models might introduce unexpected variability in the results, which ultimately affects the interpretation of the tracer kinetic estimates. On the contrary, multi-blood is experimentally and biologically informed. The main limitation of this work are the use of a single PET tracer and the inclusion of two independent sets of subjects. Further studies on this topic can be performed with multiple tracers and in the same participants with their blood measured with both types of samplers in the same PET experiment. Thank you for your attention. If you have any questions, please contact me at the email shown on this slide. I will be happy to share with whom is interested the details to adapt multi-blood to PET-MR data.